Hi, I'm Yazin. My other members are Lau Jiaju and Dashini. We are here to present you Ponte Morandi collapse, which happened in 14 August 2018. First, let's see our introduction. For the overview, on 14 August 2018, the Ponte Morandi in Genoa, Italy dramatically collapsed during a heavy rainstorm, resulting 43 people died. This wasn't just a tragic accident, but it became a wake-up call not just for the Italy but for the world. The significance of this incident extended well beyond the tragic loss of life. It exposed major gaps in infrastructure maintenance, sparked intense public outcry, and paralyzed a key artery in Europe's transportation network. Economically and socially, Genoa was deeply impacted, but symbolically, the collapse represented something even greater, a visible sign of Europe's aging and often neglected infrastructure. Let's take a quick look at the main events that led to the tragedy. Investigators identified corrosion in the southern stay cables, a critical failure point. There were also signs of possible structural fatigue and speculation about a lightning strike at the moment of collapse. Combined with pure maintenance accountability and a lack of structural redundancy in the bridge cable stay design, the disaster was tragically a failure waiting to happen. The first impact of the incident is the human impact. There were 43 fatalities with victims from multiple nationalities. As you can see, the pie chart here shown the 43 deaths, which come from different countries. Survivors describe the scene as traumatic. One man incredibly survived a 30-meter fall. Over 600 residents from nearby buildings had to be evacuated, many permanently. The emotional toll was immense, with some families even refusing to participate in state funerals. Next is the environmental impact. The collapse sent tons of concrete and steel debris into the Pozzolero River, raising concerns about water contamination. Rain-swollen conditions worsened the spread of debris. Emergency clean-up operations had to account for hazardous materials. Controlled demolition efforts had to carefully manage dust, vibration, and runoff, with long-term ecological monitoring continuing well after the event. Moving on to the infrastructural impact, the bridge was a vital link on the A10 motorway. Its loss severed a major European transport corridor. Rail lines below were damaged, local industrial zones disrupted, and homes were destroyed. The city's economy suffered greatly. Within a year, the entire structure was demolished and replaced by the Genoa St. George Bridge, which opened in August 2020. Last is the economic impact. The financial toll was severe. Losses ran into the hundreds of millions of euros, including reconstruction costs, business interruption, and emergency response. Shares of Alancia, the company responsible for the bridge, plummeted by 25% in just 2 days. Genoa's port, a critical logistic hub, was paralyzed, and taxpayers bore the burden of urgent national infrastructure inspections.
So, good day, Doctor. I'm Lojasu. So, I will be presenting the track of corrosion that happened in the Ponte Morandi bridge. So, the bridge collapsed because of the pitting corrosion. So, pitting corrosion refers to a localized form of corrosion by which small cavities or small holes are produced in the material or on the surface of the metal. So, the bridge main component, which is the steel cables that encase bridge rest, concrete will expose to the moisture and chloride ion due to missing ground in the protective ducts. So this localized attacks lead to severe pitting on individual steel strengths, drastically reducing their cross-sectional area and strength. So over the time, this corrosion weakened the cables to the point of fracture, contributing directly to the collapse. So for the mechanism of corrosion, let us take a look of the electrochemical reaction. So anodic reaction refers to the metal loss. So this occurs at the site of the P where iron atoms in the steel lost electron, oxidize and beginning to dissolve as ion into the environment. So on the other hand, the cathodic reaction refers to the oxygen reduction. So the dissolved oxygen reacts with the water and also the electron to form the hydroxide ion. This reaction maintains the flow of electron, keeping the corrosion process going. Inside the pit, acidification takes place, and then the iron ions hydrolyze, then producing the hydrogen ion, which is acid that lower the local pH inside the pit. So the oxygen is cut off inside the pit, so the protective oxide layer cannot be reformed. So the corrosion rate inside the pit becomes much faster than on the surface. There are also several environmental factors that cause the corrosion. One of them is humidity. So the bridge was located in the Genoa, Italy, a coastal city exposing to marine. So there is high relative humidity accelerated the corrosion, and also inside the cable the trapper moisture create a long-term corrosive environment. Sea air contain chloride ion, and we know that chloride are extremely aggressive and can penetrate the protective oxide layers on the steels, initiating the pits. Another factor is the pollution and the acidic rain. So Genoa is also a urban area is exposed to the industrial and the vehicle emission. So these pollutants mix with the moisture to form the acidic rain. So it's lowering the pH again and contributing to metal surface attack. Acidic condition inside the pits accelerate the ion dissolution and worsen the corrosion circle. So for the perspective of the material property, type of metal is also one of the main factor that need to be concerned, because like this case, the steel cables is in case the pre-stressed concrete, so it has good tensile performance but are more sensitivity to the localized corrosion such as pitting and stress corrosion cracking. So these cables are really rely on a tensile or siphon to resist the corrosion. So if this layer is broken, the bar steel is exposed and vulnerable to corrode attack. And then another reason is absence of failure of the protective coating. So inspection revealed that many cables in this bridge were ungrounded or have missing or incomplete grout. So this left the bar steel exposed to the moisture and chloride directly inside the ducts. So without the grout, there are no alkaline environment to maintain the steel specification. Furthermore, the design complexity and material inaccessibility. So this bridge design feature A-shaped towers, which refers to the picture, and also the internal cable duct, so which make the inspection and maintenance difficult. So many structural compounds were not directly visible, so meaning that the damage could develop silently over the decade. So next is the flow of the incident. So at 1967, the construction of bridge is complete, and then about the 1990, so the visual inspection of piers 9 and 11 revealed so there are missing ground in concrete and also corrode at lost steel strength. So at 2015, so follow-up inspection confirmed that worsening of corrosion cable steel, especially on the piers 11, shows severe deterioration and strength fractures. And 2017, so the structural dynamic test showed that asymmetry of vibration mode, and then only pier 11 have undergoing earlier reinforced with external cables. The retrofitting for pier 9 and 10 was not complete before the collapse. So on August 14, 2018, the bridge collapsed. So that they have a heavy rainstorm, so the failure began when the soft cable stay of pier 9, which have been severely weakened by the pitting corrosion, snapped. This sudden failure caused the central span of the bridge to fall, dragging down an approximately 100-meter section between pier 9 and 10. So after that, at 2020, the building or recovery of bridge is done, and the new bridge is constructed in record time with modern material and enhance the corrosion protecting. So the natural scrutiny of the aging infrastructure in Italy also increased.
Hi, I'm Rashi Nayak. Today I'm going to talk about other factors. First, we're going into the environmental condition. Environmental conditions significantly contribute to the collapse. The structure faced decades of harsh weather such as rain, humidity, and weather temperature change that slowly washes down the material. Being near to the cause, salty air speed up the corrosion of the metal part. On the top of that, freeze-thaw cycle caused crack on the concrete, and water infiltration weakened the protective layer around the steel cable, making them more vulnerable to failure. Now is about the design flaw. The bridge has several critical design flaws. First, the cable stay hybrid design used pre-stacked concrete stay encased in concrete, which made it hard to inspect and detect corrosion. Secondly, there was a lack of redundancy. If one element failed, the entire structure was at the risk of collapse. Lastly, although Morandi design was innovative, it was unproven and required complex, expensive maintenance that wasn't constantly carried out. Bridge used pre-stressed concrete with embedded steel cable, which was innovative at that time, but not ideal for long-term exposure to a marine environment. Its lack of corrosion-resistant material and protective coating. The concrete was porous and prone to cracking, which allowed water and salt to seep in and reach the steel cable. This accelerated corrosion. In addition, some reports noted material weakness in the cable themselves, making them more vulnerable to fracture. Let's talk about operation maintenance. Although maintenance was carried out, critical repair was delayed or insufficient despite early warning. Reinforcement added over the year may have been poorly executed, failing to address the poor root cause of the damage. The enclosed stay cable were also hard to inspect, so the internal weakness were unnoticed. On the top of that, traffic volume and weight had been increased significantly since 1960s, placing stress far beyond what this bridge was originally designed for. Finally, there was no advanced monitoring system in place to detect internal damage or warn of potential failure. Inspection and non-destructive tests were carried out, like ultrasound, cellulometric tests, and endometric to monitor the bridge condition, especially stress in pre-stressed steel cable. However, since the cable were encased in concrete, detecting internal corrosion was extremely difficult. As a result, structural damage often went unnoticed. In 2017, structural health monitor and vibration tests by the Polytechnic University of Milan revealed irregularities and signs of corrosion indicate growing internal damage. Back in 1979, designer Riccardo Morandi warned that sea, air, and pollutant can cause corrosion. He recommended that regular rust removal, filling damaged area with exportive resin and coating with chemical-resistant elastomer. However, by 1992, severe corrosion was found in the stay cable of structure 11. About 30% of the steel were exposed due to the poor concrete coverage. This led to urgent maintenance and the replacement of two stay cables. While the maintenance was performed over the years, critical issues remained unresolved. In the 1990s, only the eastern stay of one pier was straightened after the corrosion was detected. No similar work done on the other two piers, including the one has eventually collapsed. In February 2018, report revealed that 10 to 20% of corrosion on the steel rod under the road, but the planned reinforcement work has not started by the time the bridge collapsed in August 2018. Last part, let's talk about the human error during the manufacturing. There were key errors in the material selection during the construction. The bridge used pre-stressed concrete to protect steel cable, but this encasement made internal inspection very difficult, allowing corrosion to go undetected. Report also suggests the concrete was not mixtured incorrectly, affecting its viscosity and durability. This material and manufacturing force significantly weakened the structure over time, contributing to long-term vulnerability.
In 1979, designer Riccardo Morandi warned of the need for constant maintenance to counter rust and corrosion on the bridge he designed. Despite his clear recommendation, proper action was not taken. Over the years, maintenance efforts were either inadequate or inconsistent. Visible signs of weakness were overlooked, and early warnings from experts were largely unheeded. Specialists now believe that with regular inspection and timely repair, the tragic collapse would have avoided.
Inadequate quality control lead to the use of low-strength concrete weakening the structure from the start. The poorly designed and maintained drainage system cause water build-up, accelerating steel corrosion. These issues together cause the bridge gradual weakness and highlight the need of strict construction standards and maintenance.
One of the suggestions for the prevention is using improved materials. Traditional materials like regular steel are prone to corrosion, especially in coastal or industrial environments like Genoa. We now have access to corrosion-resistant alloys, fiber-reinforced polymers, and ultra-high-performance concrete that can greatly extend the life of bridge structures. These modern materials also require less frequent maintenance, reducing long-term costs. Next is the better design practices. Future bridges must implement redundant structural systems to prevent total collapse from a single failure point, integrate modular and easily inspectable components for long-span bridges, and incorporate hydrological impact modeling in flood-prone areas. Another suggestion for the prevention is the enhanced maintenance protocols. Proper protocols could have flagged warning signs earlier. We recommend implementing manual annual inspection by third-party certified engineers, establish national infrastructure databases, 4. Track the bridge health over its lifetime, and also apply the predictive maintenance algorithms using historical degradation data. Last, the suggestion for the prevention is the advanced monitoring technologies. Technology now offers us a proactive solution, real-time monitoring. Installing smart sensors within bridge components can detect stress, vibration, and corrosion as it develops. Technologies like drones, robotic crawlers, and even satellite imaging, like the NASA analysis after Morandi, can detect tiny deformations before they become catastrophic. These tools allow for predictive maintenance rather than reactive repairs. Lastly, there are 5 similar cases in the world. First is the Tacoma Narrows Bridge collapse in Washington, USA. It happened in 7 November 1940. It caused by aeroelastic flutter, pure wind design concentration, and resonance. Next is the Westgate Bridge collapse in Melbourne, Australia. It happened in 15 October 1970, caused by the faulty construction method, communication failure, and structural instability. Next, move on to the higher urgency walkway collapse in Kansas City, USA. It happens in 17 July 1981, caused by the fault design change, construction error, lack of proper review. And the I-35W Mississippi River Bridge collapse in Minneapolis, USA. It happens this 1st of August 2007, which caused by the design flaw, metal fatigue, inadequate inspection, and the deferred maintenance. And lastly is the Kollam Punella Bridge collapse in Kerala, India, which happens a few weeks before the Ponte Morandi, which is in 24 July 2018, which caused by the structural failure due to the poor material quality, flood, and erosion effects. So, for better understand the significance of the Ponte Morandi collapse, it's very important to compare it with the other notable structural failures around the world. Before ending our presentation, here are our references. Thank you and bye.